welcome to this video. In this video, we'll be looking at the modulus function and how to solve equations involving modulus functions. But before we jump into the depth, I want to show you how intertwined are the modulus function and the quadratic function. So if we quickly have a look at the Desmos graphic calculator, I've created a couple of examples for you, and I suggest you type in yourself these two lines of code and get yourself some variables A, B, C, and D, and have a mess around and look at the problem and see how we can change these variables and how the shape of the graph changes accordingly. So if you pay attention to the variable C here, it's inside the bracket, inside the square bracket, and that's basically this intercept on this line. So if I have a slide around the value of C, as you see here, both the quadratic is in its completed square form and the modulus function move together. And if we change the variable B here, that's the coefficient of X. So that should change the gradient of the line. And if we change the value A here, that also changes the gradient of the line, but in a different way. I let you have a look at that. A is related to the y values, and B value is the gradient related to the x values. Anyway, you can have a look at that in your own time, and you realize what's the connection between the modulus function and the quadratic form. After all, the reason that they are interconnected is that both the modulus function shows us the positive version of the graph. Also, when you square any values, that also turns into positives. So that's why they are exactly one and the same. If you notice the point of the vertex of both graphs, vertex being the point where the line has a kink, and the maximum or minimum of the quadratic, they share that point on them on both graphs, and that's determined by the values C and D. If we increase the value of D, the y value goes up and down. If we change the value of C, as you saw, the x value goes left to right, the x coordinate of the vertex. So let's have a look at a couple of examples here. In this first question, we've been asked to show that this equation does not have a solution. So what you can do every time you see modulus function, you can also think of it as a square bracket. So we could write that as 3x plus 4 inside the square bracket being equal to x minus 2. Now, I'm not saying they are the same thing, but the solution to this equation would be the same as the solution to that equation. So if we can manage to show that this line doesn't have a solution, we have shown that that equation in the question doesn't have a solution. So let's expand the bracket and see what we get. So expanding the bracket on the left side, we will have 9x squared plus 2 times 12x. That's a times sign here, and my x is curly, so this is just the multiplication, and we'll have a 16 there. And I'm just going to keep the x minus 2 on the right for now. So bringing the x minus 2 to the left and multiplying this, take away a 24. The 24 minus 1, I'm just going to write it in front of the x, and we'll have a 16 plus 2. 16 plus 2 is going to be 18, and that will make it 0. So this is simply 23. So we have this quadratic that is in terms of x only 23x plus 18 equal to 0. And now we can, we look at the discriminants. If you remember the discriminant b squared minus 4ac, we want to calculate and see whether is this positive or negative or 0. So obviously we'll have 23, that's n squared minus 4 times 9 times 18. And if you put that on your calculator, we'll get a value of negative 119. So let me just write that as, now that we know the discriminant is negative, we say that this equation doesn't have any solutions. Therefore, our original equation in terms of the modulus sign doesn't have any solutions either. We not considering the graph of this function, these two lines, so we simply prove it by algebra. Now I'm going to solve this other equation, part B. Well, here it's best to write a little conclusion that to say that does not have any solutions. So to answer part B, we can use the same trick that we used in part A. We can write this as a square and we will write this as a square because now x minus 2 does have a modulus sign here. So expanding the bracket on the left will give us the same answer that we calculated in part A. So I'm not going to go through the same working out again. We had actually 24x. If you remember up here, this line here, we ended up with 24, 23. So I should have been careful there, plus 16. And on the right hand side, we'll have x squared minus x times negative 2 times 2 is minus 4x plus 4. Now we're going to collect the all variables on one side of the equal sign. So 9x squared minus 1x squared gives us 8x squared. 24x plus another 4x will give us 28x. 16 minus 4 is going to give us 12, and we can write that equals to 0. Now, the largest factor, we can divide everything by 4 just to have a little simpler equation. 28 is 7x plus 3. Now, we can factor this out into two brackets and we will have 2x and x here, plus 3 here and a plus 1 here. If I quickly expand that, we'll have 6x plus 1x, which is 7x, and that's correct. Okay, so this means that x is either minus 3 or x equals to a negative half. And of course you can find the y values in your own time. So this shows that the intersection of these two graphs has two intersection points. So to find the y value, obviously our y values will be the negative, y values have to be also positive. So 3x, if we take x1 here, 3 times minus a half plus 4 will give us negative 3 over 2 plus 4, which is 2.45. And this is for y1 here. So this coordinate is negative half, comma 5 over 2. And if we substitute the second point, 3 times minus 3 plus 4 is minus 9 plus 4, which is minus 5. But we take its absolute value because sine, so 9 plus 4 to 5. Or minus 5 is absolute sign, so we'll have a negative 3 comma 5. So that's the actual two answers of this equation, in these two equations. So I hope you found that helpful. I'll see you in another video.